In this video, we are going to solve an exercise about lines and circles. We are given a circle C of center O and radius 2. This is the notation of this circle. So here we put the center and here we put the radius. This is the name of the circle. Whenever we see this notation, it means there is a circle. The name is C, center O, and radius 2. OE is equal to 4 centimeters. The circle of diameter OE, this red circle, will cut the C in S and N. A circle of diameter OE, then the radius will be also 2. Now we want to show that SON, the angle here, is 120 degrees. How to prove this? In fact, whenever I want to show something, I must ask myself, how can I prove this? In order to prove SON 120, I can think of proving SOE 60 and EON 60. So how to prove SOE 60? I can prove SOE semi-equilateral and ONE also semi-equilateral. How to prove this triangle semi-equilateral? Let's explore the nature of these two triangles. What do we have information about SOE? In fact, OSE is a 90 degrees. Why? Because it is an inscribed angle in the red circle facing diameter. So we have a 90 degrees here, and OS is a radius, so it is equal to 2, and OE is equal to 4. OE is the hypotenuse. As you see here, this side OS equal to, which is half the hypotenuse OE. So we have a right triangle and a side being half the hypotenuse. Here we should remember the rule of a side facing 30 in a semi-equilateral triangle. Then this triangle is not any right triangle. It is a special one, which is a semi-equilateral. So, and this side is facing the 30 angle. So it is a 30-60 triangle, then we got a 60 here. Similarly, we can prove also here, getting 60 plus 60, we can add up. So how to write this? First of all, we say since OSE is equal to ONE equal 90, inscribed angle facing diameter, then the triangle SOE and ONE are right at S and N respectively. Then EO, but here we say but EO is 4 and OS is 2 and ON is 2. Then we can note that this side OS is equal to the hypotenuse over 2 and ON also equal hypotenuse over 2. Then OS and ON are sides facing 30. Then we can conclude that these two triangles are semi-equilateral, SOE and ONE. So we got a 60 degrees here, SOE equals 60 and EON equals 60. We can add up in order to get SON. So SON will be equal 60 plus 60, which is 120. Now, in order to prove that EN is a tangent to C at N and ES tangent to C at S, we ask ourselves how to prove tangent. How to prove tangent? In fact, there should be a 90 with the radius. Do we have a 90 with the radius? In fact, yes. So we can say since ONE equal 90 already proved and ON is a radius. Why it is a radius? Because it is a segment joining the center to a point on this circle. Then EN is a tangent to C at N. We have to be specific. It is tangent to which circle and at what point, making 90 with the radius. Similarly, we can say that ESO equal 90 degrees proved and OS is a radius. Then ES is a tangent to C at S. Here we want to calculate ES and EM. In fact, ES or SE is a side in triangle SOE, which is proved to be a semi-equilateral one, and it is a side facing 60. So, in a semi-equilateral triangle, the side facing 60 is equal hypotenuse radical 3 over 2, and we are given the hypotenuse OE to be 4. So we can calculate SE. Similarly, ONE is a semi-equilateral triangle where NE is a side facing 60 angle, then it is equal hypotenuse radical 3 over 2. So we can say, since triangle SOE and ONE are two semi-equilateral triangles proved, then ES is equal to hypotenuse radical 3 over 2, and the hypotenuse here is OE. Hypotenuse is the side facing the 90, which is OE, and it is equal to 4. So we remove OE and replace it by 4. Since 4 radical 3 divided by 2 can be simplified, we can get 2 radical 3. Whenever we have 2 nothing radical 3, nothing means multiplication. We can simplify by 2 up and down, thus getting 2 radical 3. Since OE is given to be 4 centimeters, so the unit is centimeter, we can write centimeter. And why we use this rule? Because ES is the side facing 60 angle. Similarly, En equal hypotenuse radical 3 over 2, and in triangle ONE, the hypotenuse is OE, so we can replace the hypotenuse by OE, then replacing it by its value 4, dividing by 2, the numerator and the denominator, to keep the equality true, thus getting 2 radical 3. Then we can say that ES and NE are equal. Now we want to calculate the area of ESON. Well, looking at this quadrilateral, one would realize that it is not a regular one, it is not a square, it is not a rectangle, it is not a parallelogram, it is not a trapezoid. So it is just a scalene quadrilateral. It is a quadrilateral because it has 4 vertices. So how to get this area of this trapezoid? Since it is not a rule, we can think in another way. Getting the area of triangle OSE, adding it with the area of ONE, we can cover all the area of OSNE trapezoid. So simply we can say the area of ESON is equal to the area of OEN plus the area of triangle OSE. And the area of a triangle is equal to height times base over 2. But here, special case, we have a right triangle. So OS can be considered the height and SE can be considered the base. And we can say leg times leg over 2. So no need to get a height from issued from the 90 angle. So we can say, similarly in the other triangle, ON times NE over 2, and here OS times SE over 2. And ON is equal to 2 and OS is equal to 2 radii of the circle C, and the circle C has a radius of 2. Then we can write, instead of ON2 and instead of OS2, we have just proved that SE and EN are equal to 2 radical 3, substituting them, then making normal calculations. Note that 2 and 2 can cancel up since we have multiplication. 2 radical 3 plus 2 radical 3, we can get 4 radical 3, adding up same radicals, and the unit is centimeter power 2. Here we want to prove that the two triangles ESA and ENK are congruent. It means the red triangle and the blue triangle are congruent. And we have to determine their homologous elements. So we have to think step by step. How to prove congruent? In fact, in order to prove the blue one congruent to the red one, we have to find a side from the blue equal a side from the red, or an angle from the blue is equal to an angle from the red according to a side, thus getting 3 sides from the blue equal 3 sides from the red, or angle, side, angle, or side, angle, side. Let's see what we can check here and what we can find. We already proved that SE is equal to EN equal to radical 3. So SE is in the red, is equal to EN in the blue. So we find a side from here equal a side from here. That's great. What else? In fact, we can say that KNE is equal 90 and ASE is equal 90 also. So we find that an angle here in the blue is equal to an angle here from the red. So till now we have a side from here equal a side from here and an angle from here equal an angle from there. So we have founded angle side. Can we find another element? In fact, if we look carefully, we can realize that KEN is equal to AES as a common side, as a common angle. So it is the same angle here. If you can check it up, it is red and blue at the same time. So we can say that in the red triangle, we have angle, side, angle. And as you see, the side is lying in the middle between the two angles. Let's check in the blue one. We have angle, side, angle. It is very important to prove that the side is between the two angles, else we can't prove congruent. So how to write them? We can say in two triangles, we have to state where we are. In two triangles, ESA and ENK, we have ASE equal KNE equal 90, already proved, so we got an angle here, and SE is equal to NE equal 2 radical 3, already proved. Here it is a side, and SEA is equal to NEK as a common angle. Then the two triangles are congruent by angle, side, angle. This is how we prove congruent. According to the homologous sides or the corresponding sides, we can get the sides from the angle here. For example, ASE. Where is ASE? This is ASE here. What is the opposite of this angle? It is AE. So AE is equal to what? KNE. Where is KNE? KNE. What is the opposite of this? It is KE. So we can say that EA is equal to EK. The property here of finding the congruent or the homologous sides, whenever we have two equal angles, we will get two equal sides. And what are these two equal sides? They are the opposite of these angles. So you put your hand here. This is the angle S. The opposite of it is AE. And here the angle N. The opposite of it is KE. So AE is equal to KE. And if you wrote the angle correctly according to the triangle, you can just jump. AE is equal to KE. And here SA is equal to NK. Let's also check it on the drawing. This angle E in the blue is facing NK side, and this angle here in the red is facing AS. So AS or SA is equal to KN. This is how do we get the homologous elements. Here we are wondering what is the nature of triangle KEA, this big triangle, and of course we have to justify our answers. So we check out the sides and the angles of this triangle KAE. In fact, we already proved that KE is equal to EA by homologous sides. Then this triangle is isosceles in the first place. But we must also keep on wondering and asking ourselves, what if this triangle is more than isosceles? In fact, it is more than isosceles. It could be an equilateral. So let's check if we have a 60 angle somewhere, either on the K or angle or the A or the E. But of course, it's going to be on the E because we already worked here in this zone. This angle E, which is KEA, is equal to SEO plus OEN. And we already proved that these two triangles here, OSE and ONE, are semi-equilateral. So we have a 30 here and a 30 here. So we can add up together in order to get a 60 angle. Thus, we have KEA and isosceles having a 60 degrees angle, then this triangle is an equilateral triangle, being isosceles with 160 angle. So since KE is equal to EA proved, then this triangle is isosceles at E, having two equal sides. But we already proved that SOE and ONE are two semi-equilateral triangles. Then SEO is equal to 30 and OEN is equal to 30. So KEA is equal to SEO plus OEN, adding up, getting a 60. Then the triangle KEA is an equilateral triangle, being isosceles plus one plus having one angle, which is 60 degrees. I want you to note that this angle E here, we can call it KEA or SEN. But here we are saying KEN because we are talking in triangle KAE. So this triangle is an equilateral triangle. Now we want to prove that AK is a tangent to circle C. In fact, looking at this figure and in this big triangle and how is the circle inside it, you can say that this circle is inscribed in this triangle. And what is the center that gives me an inscribed circle inside the triangle? It is the incenter, which is the point of intersection of the three bisectors. So if we can prove that O is the incenter, then we can say that this circle is inscribed in this triangle. And we know that when this circle is inscribed in this triangle, the three sides are the tangents to this circle. And we already proved that KE and EA are two tangents to this circle. Then for sure AK will be the third tangent. So let's prove that this incenter here, this O is the incenter. How to prove this? In fact, we have to prove that O is the intersection of bisectors. It is enough to find two bisectors because we know the third one will pass through O because the three bisectors are concurrent. So no need to prove three bisectors, only two. We already know that SEO and OEN is equal to 30. So OE is a bisector. So in triangle KAE, we have OE is a bisector for KEA angle. We have a bisector here. Now let's prove another bisector, either KN or AS. In fact, AS is a height because we have a 90 here, or AS is perpendicular to KE. So AS is a height, but I want it to be a bisector. I remember that AS is also a bisector. Why is that? Because in an equilateral triangle, the height is the median, is the bisector, is everything, is the perpendicular bisector. In an isosceles triangle, issued from the main vertex, but this is an equilateral triangle, so even more. So any height is a bisector, is a median, is everything. So in an equilateral triangle, the height, the median, the bisector, and the perpendicular bisector are all confounded. So AS is a bisector and OE is a bisector, then O is the incenter. It is the point of intersection of the three bisectors. But we already proved that AE and KE are tangents to this circle. Then we can say that this circle is inscribed inside the triangle. Then Ka or Ak is the tangent to this circle.